Right, in this video I'd like to introduce this application of inner product space to geometry. Inner product carries more information than just the distance or metric between the two vectors or position vectors, but that's what we're going to focus on here. We can introduce this application purely in geometric context, but if we use this relativity phenomenon, it's a lot more fun. So let me use this example. Suppose this person A is here, and he's at the center, and he's observing a particle is moving from this position, -2, 0, to +2, 0. So that was person A's observation in this world. But we're looking at this system from a distance, but this is our observation. Person A is sitting there, and the particle was not at -2, 0, but it was actually -1, 0 over here, and moved to close to 2, 0, but a little short. So we don't have that information, but we have that information. And then inner product is going to help us to figure out the distance that, like I said, is metric, distance between this point and that point. So it looks like actually shorter than what the person A is observing, but inner product will help us to retrieve that information. Distance from here to there is not really something close to +3, but we're going to conclude that it's going to be actually 4. Not knowing this complete information, but with that extra gadget called inner product. So for this example, I have formulas to create this one according to that. The inner product matrix is given by this symmetric real matrix. So we compute this directional vector. If you subtract this vector from that vector, that's going to be this directional vector, and inner product to itself through this matrix will give us a distance squared. If you put the square root, then we're going to have a different interpretation of the length between these 2 points. That distance is actually the distance the person A is perceiving. We make it clear in here with this inner product, and we don't have the position of this beginning of the particle position and end of the particle position, which was this. But what we see here is this location, and parametric equation I wrote down is what we see. By using that parametric equation and inner product, we could retrieve the distance between this particle travel and the coordinate system of the person A. In general, if the path we're looking at is not straight path, for example, if a circular path from here to there, and we have to kind of divide those paths into a smaller section, and then you can see easily we enter integral by doing that. Each time when you do that, there's a little different direction of a segment. That direction is important, so that direction is measured by this velocity vector or directional vector by differentiating the parametric equation we see. And that's okay. Only thing you have to be careful about is when we calculate the length of that vector there, we have to use that inner product, which is this one in here. So we have coordinates x and y coordinates here, but we're not going to dot it to itself to calculate this one. We're going to go through that matrix that I showed you down there. So if you have the parametric equation of that path, you go through that matrix A, and this will measure this distance +4 for this case. The one example I just showed is more close to the special relativity phenomenon. So the person A is moving at a constant speed, or there's no strong force involved, something like that. But suppose this whole system is accelerating, or there's a strong gravity affecting it here. Then things are getting more complicated, so I use this lever in here to increase the level of this curvature. I call this gravity level. So again, to guy A, this thing just goes straight from -2, 4 to +4. But what we're observing this time, it's not a straight line starting from right above this -2, 0, going like this. This is our observation. So again, we have to use this inner product, different inner product, to compute the lengths in every part. We have to approximate that. But this time, the matrix is strange. Over here, it turns out, when you're close to -2, 0, the inner product matrix is depending on where you are. So if you're -2, 0, you have to plug in -2, 0 to this inner product, so you get a 1 matrix. So when you're estimating a straight path after you're kind of divide and approximate it, you have to use a certain matrix. But if you go over there, which is almost like 3, 1, then you have to plug in 3, 1. All these 4 entries are depending on your location, so you get a different matrix. And when you're estimating the length around here, you have to use that matrix, different matrix. So this formulation is still true. The only different thing is that this matrix in this inner product is changing as this t changes. If t is different, we're looking at the different positions here. That position will give you a different matrix. So according to the formula that I use to create this example, that inner product matrix look like this. If you look closely, there are x and y's involved. And that path turns out to be in this formula. Now this involves t squared, so it's actually a quadratic equation, quadratic parabola, part of a parabola. So each position, x and y, is parameterized by t. So if you plug in this thing in terms of t, in this place of x and y in here, this inner product matrix is parameterized by t. So when t equals 0, it's here. T equals 1 somewhere here. That uses different inner product matrix. So that a is no longer constant 2 by 2, but parameterized by t going in there. And no matter what, this whole thing is a massive expression of one variable t. So that's how you calculate this integral value. And that integral value is just supposed to be +8, because it's going from -4 to +4. So this is more of a little baby example or demonstration of the mathematical flavor of general relativity. Right, this is my Mathematica Animation. Gravity level is 0. You can see the matrix is constant, and that's a straight path that we're observing down here. As you can see, it's this degree 1 polynomial in t. So if I increase the gravity level a little bit, so you can see that our observation is no longer a straight path, and we can see that it's quadratic down there, and the matrix is all depending on x, and it's really massive. So if I change the beginning and the ending portion of the straight path in the person A's coordinate system, you can see the curvature in there as you change, and you can see in some parts it's more curved than the others, and things like that. And you have to use this massive matrix to calculate the correct distance from our observation. So I hope that was a good example that shows that how inner product is used to carry the geometry that's distorted from our observation. Not only can be used for arc length, but it can be also used for areas and the volumes of any higher dimension, and which is the main part of the calculation in physics as well, and relativity.